Welcome to Yaka Digital Network. Today, we're exploring the chemical processes driving large-scale manufacturing and sustainable industry. Uganda's economy is deeply rooted in its soil. Millions of citizens rely on the daily physical harvest of cash crops like coffee and maize to support their families and drive the national market. But maintaining this high agricultural output depletes the soil over time. To replenish it, farmers need reliable access to fertilizers, and right now, the country spends a massive amount of capital importing these chemicals from abroad. You can't solve a nationwide soil deficit with a few laboratory beakers. You need to scale up to massive industrial-level chemical manufacturing to produce enough material to actually meet the demand. To reach that scale, industries rely on two specific methods: the Haber process for producing ammonia and the contact process for manufacturing sulfuric acid. Mastering these two industrial pathways allows local factories to produce their own fertilizers affordably, directly increasing domestic food security and keeping capital inside the country. Let's look closely at the Haber process. The main objective here is to pull atmospheric nitrogen and combine it with hydrogen to create ammonia, the core building block for modern fertilizers. Nitrogen and hydrogen are routed into a high-pressure compressor. This reversible reaction is exothermic. By Le Chatelier's principle, high heat lowers the ammonia yield. So engineers compromise, keeping the temperature at 450 degrees Celsius while crushing gases under 200 atmospheres. But even with that pressure, the moderate temperature makes the reaction too slow to be profitable. What missing element can speed up this specific reaction without destroying our yield? 3, 2, 1. The answer is an iron catalyst. Passing gases over this iron bed makes the reaction happen quickly and efficiently. Nailing this exact balance of pressure, heat, and catalysis is what makes it possible to mass-produce the ammonia needed to fertilize thousands of acres of local crops. Next is the contact process. This is the industrial method used to manufacture sulfuric acid, a substance so vital to global manufacturing, it's often called the king of chemicals. This schematic maps out 3 stages. In the first chamber, raw sulfur burns in air to create sulfur dioxide. In the second chamber, sulfur dioxide reacts with more oxygen. This requires a vanadium 5 oxide catalyst to secure a high-yield conversion into sulfur trioxide. Finally, that sulfur trioxide gas is dissolved into concentrated sulfuric acid to form a thick liquid called oleum, which is then carefully diluted with water to create pure, usable sulfuric acid. Generating thousands of liters of this acid domestically feeds directly into other manufacturing sectors. For example, it provides the precise chemical component required to assemble car batteries right here at home. This entire industrial sequence is an exercise in value addition. When you take basic raw materials and use chemistry to transform them into finished products like urea or ammonium nitrate fertilizers, you generate significantly more market value than you would by simply selling raw, unprocessed crops. But operating at this scale introduces serious risks. Massive industrial manufacturing inherently produces highly concentrated, dangerous chemical waste. If a plant running the contact process fails to capture stray sulfur dioxide gas, it vents directly into the atmosphere. This creates acid rain, which actively strips nutrients from the soil and damages surrounding forests. The math is straightforward. The immediate economic boost of cheap fertilizer is completely erased if the resulting chemical pollution renders the surrounding farmland toxic. The same vulnerability applies to our water sources. Releasing untreated, acidic wastewater from these factories directly into rivers or lakes quickly devastates local fish populations and degrades the fresh water supply. To prevent this, modern facilities require massive infrastructure dedicated to mitigation. They use large-scale neutralization tanks to chemically balance the pH level of the wastewater before a single drop touches the outside environment. The most efficient plants operate on a circular economy model. Because reactions like the Haber and contact processes are highly exothermic, factories can capture the intense waste heat they generate and recycle it to power other parts of the facility. True industrial development in Uganda requires mastering these complex chemical processes alongside rigorous, non-negotiable protections for the land and water. Thank you for learning with Yaka Digital Network. Be sure to review your supplementary notes and join us in the next module to continue your studies.